Okay. Um, oh, that's right. So you missed out a couple of important details of the supernova explosion
Okay.
mechanism. The most important being that the core collapses.
Okay. Well,
Um, and the order of things. I mean, it's the let's see
I
if
really did just say that the outside just explodes out and the core just kind of
yeah,
stays there. Okay.
yeah.
Core collapses, allowing the outer layers to fall inward, rebounding and causing the explosion.
It's just a simple cartoon. What's
This is Jason Kendall. Welcome to the next of my introductory astronomy lectures. Today we're going to be talking about supernova. And supernovae are exploding.
um, okay, this is weirdly hard to find, so
Okay.
um, we'll push that back. Um,
Sure you had one in your presentation. Oh,
well, I'm sure I had a cartoon picture, but I wanted an animation. Um, anyway, okay. Did I can't remember whether you actually mentioned neutron stars have a solid crust and liquid
I
core.
did.
You did.
Yeah,
Okay,
this time
good,
I did.
good.
Yeah. Yeah, I said that the crust comprised of solid material and the core was mostly
Yeah.
liquid.
And did you mention, because you mentioned the lattice soon after this. So
Yeah,
do you
I
mention
mentioned that it was
here?
organized in the lattice pattern,
Yeah,
but I went into detail when we went
right.
through the
Okay.
Should I say that more up here and say a picture of this lattice will be shown later?
No, you can just say the nuclei are arranged in a crystal lattice. And that's all you need to say. Um, okay. Next slide. So so I think you said the other star expands and contracts throughout its life. It's expand. I mean, it's like our sun. It'll sit there for 5 billion years or so, and then it'll gradually expand into a red giant.
Right.
There's no contraction.
Oh,
right. It'll just gradually expand.
Oh, I thought that this. Okay, I thought that this like stars just kind of.
Some stars do that, but
Okay,
no,
no,
not
okay.
that. This is just normal evolution of a star.
Oh, so as the star just progresses through its life, it
Yeah.
expands,
It
and
expands.
as it expands, the material overcomes its Roche lobe.
It fills its Roche lobe and then falls onto the star. And you mentioned that as it spills over its Roche lobe, you mentioned, I think you mentioned you mentioned that means it's then influenced by the magnetic field, but you didn't mention it was influenced by gravity.
Is it
the most
Is it
important?
gravitational or magnetic field of the neutrons?
Did you? Okay.
Yeah, okay. Should I just mention gravitational field?
Yeah, well, so
I know we're
that's
focusing on it.
the definition of the Roche lobe is
Only gravity, not electromagnetic.
the Roche lobe is the region that separates where its gravity wins versus its gravity wins.
Only mention gravitational influence.
Right.
Okay.
But I mean, there is magnetic influence in the accretion disk, but that's not part of the Roche lobe overflow.
And I obviously just confused people right now. So
right. That's okay. That's okay. Remember, it's one nucleus, not one nuclei.
Did I say that?
Yeah.
Oh, no way.
I think you said so. Make sure that you actively point to the pictures.
Yeah. I hope they give me a laser because I have mine, but you know how bright that one is. And I will just be shining my laser.
Yeah.
This,
yeah.
And then as it falls on, this gets pushed inward as a new layer appears.
Yeah. If they don't, we can find a stick.
Oh.
I think you mentioned, like the way you mentioned it, you made it sound like the heat. Like you mentioned the heat first and then nuclear reactions so the heat is the heat released in nuclear reactions. Right, so nuclear reactions happen and those nuclear reactions release heat.
Right.
Right. I mean, this is exactly what's happening in a nuclear reactor. Well, sorry, other way. It's what's happening in a fusion bomb.
Right.
But anyway, nuclear reactions release heat.
Yes. Okay, specify.
You refer to energy models several times, and I'm not sure what an energy model is.
Trying to the compressible liquid draw model.
Oh, so the model for the crust.
Yes. Was that not an appropriate word to use there?
One energy model is a model for, like, they're going to be like a model of energy. Like that seems a very general thing.
Okay. Yeah.
Like, is this just a general model for any type of energy in the universe. What is that? Sounds very I don't know what it is or what it applies to.
Okay.
Right. So it's a model of the crust is what we're talking about. Right.
Yes. Okay.
Right.
Crustal model.
Yeah. The crustal model. Okay. Yeah, I think you just made your explanation of these nuclear reactions, you made more complicated than need be by just repeatedly adding words that didn't need to be there. Did I write down an example? Like, so, I mean, electron capture, an electron gets captured by a proton, which turns into a neutron, and it releases a neutrino. Sometimes the addition of that neutron makes it unstable, and so you get neutron emission where it ejects a neutron.
Yeah, I repeated myself, I think, twice.
Yeah.
Here when I was playing.
And then you were saying, yeah, I remember you said something is like it releases the neutron to the outside. Like it's like it just releases the neutron.
Okay. Yeah.
It's obviously being released to the outside. Like what? Yeah. So it's but that's you're doing that just because it's not polished yet. Like you haven't like with practice, you kind of know what you're going to say, and that's that thing that won't happen. Okay. Go to the next slide.
You need to organize these a lot better than they are right now.
Yeah.
Because I just half-assed.
Yeah, and each term you point to, you should point to like
I think we actually just spoke about reducing this and like only showing this because it still's a pattern.
Yeah.
And it'll be a lot larger.
Yes.
Okay, I'm just gonna do that. But yes, as I'm explaining the terms, point to what they would be.
Yeah, so this is the energy of the interior of the nucleus. This is the energy of the neutrons outside. This is the electrostatic energy between the nuclei and the electrons and the nuclei and the other nuclei. This is the energy of the surface. So the dotted line represents the surface of the nucleus.
Okay. Not the
right, not the surface end. I
Okay.
mean, this is all representation of the physical thing,
Right.
not the energy of the physical thing.
Okay.
Right.
Okay.
Yeah, and then the electron energy. Oh yeah, you didn't mention what A and Z were here. As you go along for each term, you should say, okay, this term is the energy inside the nucleus. A is the number of nucleons. Z is the number of protons. U is the volume fraction. I think I feel like you said something where your definition of X wasn't quite.
I don't even mention X. I just mentioned A, Z, and X.
Okay.
Yeah, I need to introduce all that stuff here, not here.
Yeah.
Yeah.
But remember, it's only a brief
Right.
mention. Like you don't need to explain. You don't like you don't need to be like, this is the volume fraction of nuclei, which means it's the blah, 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 blah. Right, it's just like A is the number of nucleons, Z is the number of protons, volume fraction of nuclei, number of neutrons outside, density, fraction of protons, radius of nucleus, surface tension. The thing to take care of is introducing the L parameter, because this is the tricky thing, because you should avoid I think you should avoid saying skirm altogether, because it's a jargon word that people are going to be distracted by, wondering what this thing is. What you can say is, for this and this, we need a model for nuclear matter. And there is a parameter in that model that we call L that is proportional to the pressure of neutrons in the matter. And that is that is a quantity or a parameter that is not well constrained by experiment.
Okay.
And then sigma represents the surface tension, which is also not well constrained.
Yes.
Right. So you mentioned that they're both not well constrained, hence there's uncertainty. And I guess, is this a placeholder for putting in just the sigma?
Yes, actually.
Yeah. Okay.
When I was practicing this morning and last night, I realized, the flow, should I start with the outer crust and then move on with the inner crust?
Yes.
Yeah, because when I was practicing with the inner crust and outer crust, it's out of order.
Yeah.
But outer crust.
Yeah.
This. So I didn't understand much. So I understand why we don't need the outer neutrons, because the pressure just doesn't allow neutron drip at this point.
Yeah.
For the outer crust. Why is the surface energy already calculated with the nuclear mass?
Yeah.
Okay.
Yeah. So these numbers here are this plus this.
Okay. Okay.
Right. So they take into account that. Oops.
Yeah.
But in this equation so this was what I was talking about yesterday. So WAZ in the outer crust is these numbers here.
Right.
Right. But in the inner crust, those we're replacing those numbers with the numbers that our Skirm model gives us.
Right.
And that's this plus this.
Right.
So this WAZ is not the same thing as this WAZ.
Right.
So we should we should just I would subscript this one with NM for nuclear matter.
Okay.
And this for nuclear matter.
Yeah. Okay.
Right, because nuclear matter is just it's not a nucleus, it's just a sea of neutrons and protons.
Right.
So subscript these two with NM.
Okay.
So they're clearly different.
I did not. I didn't copy what you said yesterday. Well, Tuesday, when you were talking about what WAZ was. So when I was just listening to recordings, it said bulk, then surface, and then
bulk plus surface.
Yes.
So it also contains a bit of Coulomb, but so this Coulomb term includes all the Coulomb contributions. So it includes the repulsion of the protons inside the nucleus, the attraction or the repulsion between this nucleus and the attraction between this nucleus and the surrounding electrons. So there's three separate electrostatic interactions going on, and they're all in this term.
Right.
But one of those refers to the nucleus itself, which is already included in the mass table. But it's just going to get too complicated to explain that.
So
So
should
I
we
would
just
stick
do
with
away with
this.
this?
Yeah. So if you're,
I included that because I wanted to ask you if
yes.
sure.
Yeah, yeah. So in this, so W bulk is this,
Right, yes.
and
Surface is right
W
there.
surf is
Right.
this. So if
The only
you,
thing that the nuclear model introduces are these two terms that we didn't have, that we had to calculate individually because
yeah, I
this
mean, they were
order.
there. They were just already included in the nuclear masses.
But there's no specific like table for an 800 nucleon element.
Right. No, yeah. So that's we need to use our nuclear model because they don't exist. They haven't been measured. Um so yeah, so I would, I mean, you could label this bulk if you want.
Okay.
Um and then instead of W surf you can put the 2 sigma over R in.
Okay.
Just because that's what it's called here. You don't call it W surf, no. Yeah, for the outer crust, again, it's so this picture includes the neutrons surrounding
Outside,
it, which
yeah.
isn't.
I haven't been able to get any software to just blank out the blue
Right.
in the background. Um, it is just okay. All my time right now has been because our classical mechanics class.
Yeah, yeah, I
Six
understand.
problems instead of normal 3 4.
Okay.
So there's just a bit more effort that I have to
Yeah.
do. But today that'll be over and also math methods. So I should just put all my time into just
Yeah, can I
slowly.
browser? Is
Oh,
that a browser? Okay, let me pull up my one claim to fame. If I Google, oops, stop Rust. Yeah, and go to images. Here we go. My picture is one of the first setups. Oh, that's just the inner crust. Okay, that's useless then. That was a disappointment. Again, it's hard to find what you exactly want. Okay. Yeah, find. Yeah, the slide might work.
What were you trying to find?
I was trying to find a picture that is like that, but for the outer crust. Here we go. Here we go. Here's a picture I have. This would work. So outer crust, inner crust pasta. So this does include so outer crust, there are no free neutrons outside. In crust there is.
Okay.
So that would be the one to use. And you could use that for both.
Okay.
Yeah, the very simplest thing I can do is okay. I've just sent you an email with that image. It may take a sec because
Thanks.
I think it's probably like a megabyte or two. There we go. Okay.
So I'm guessing
Now you can get rid of that now. Yeah. So the nice thing is you can use that for all of these slides where you did have the
Yeah.
yeah.
Okay. So
Okay. Cool. Oh yeah, also the order. So the assumption of this model at the start is that they're arranged in a so-called Wigner-Seitz cell. So I'd be like, okay, so we're using this model called the compressible liquid drop model, which assumes that the nuclei are arranged in a repeating crystal pattern.
yes.
And that you can identify a single repeating unit that we call the Wigner-Seitz cell.
Yeah.
And then we only need to write down the energy of one of those cells. Right, so that's the important point to make. This is the energy of a single Wigner-Seitz cell, not the energy of the whole.
Right. Collection.
Yeah.
All right, good.
Yeah, in the outer crust, this is the place to show this. Like, because they're
because this is where I introduced
nuclear mass. So that is that. Yeah. Right, so you can have the table there, and it's like, so this comes from this nuclear mass data. So each of these numbers is that for that particular nucleus.
Okay.
You mentioned iron was the target element. I wasn't quite sure.
At the very bottom, yeah.
I wasn't quite sure what that meant.
I should have said we started with an iron 26.
Right. So iron 26 is at the top. Yes. So this should also be included in these slides. So instead of this, you can have you could have this. Where's control? I've gone too far. Okay, you can arrange that. So the point is that, okay, so you've introduced the model for the outer crust.
Yes.
Here are the results. Up here, we're starting at the surface. And as we move this way, the pressure is increasing. And what we're doing is we're moving into the crust. So now, because before you were trying to explain that with words,
Right.
it's much easier if people can actually see on the picture where you're going as you're going down this way. So this represents the change in the isotopes of these nuclei as you go deeper into the crust.
Okay. Yes.
And same for this. You should also have that picture somewhere on here. And arrange these.
I think I am going to try to make. Okay.
Yeah, here's what you do.
Blow this one up a bit more. And then as I talk about these, I just say if we reduce the L parameter to this will disappear, this will appear, and then the picture right here would just appear right here. Say,
can I make a suggestion?
Yeah.
Sorry. Okay. Okay. So you've got this you can still point to as you go this way. We're going into the inner crust now. And now you get by flicking from one slide to the other, they can directly see the change like kind of overlaid on each other.
Yeah.
So again, it makes a nice visual. And this is how I always do animations. I just duplicate the slides several times. It's just the easiest. Right. So the key thing is somewhere you should have clearly labeled the research question, because nowhere on these slides do you say the question we're actually trying to answer. And well, you do, it's here, but it's hidden a bit. So the point is the thing to explain in simple terms is we have a nuclear model, a model for nuclear matter.
Yes.
And the most uncertain parameter in that model is a parameter that is called L, that is proportional to the pressure of pure neutron matter.
Yes.
And then we also need to specify the surface tension of the nuclei, which is also something that is quite uncertain. And so what we want to figure out is we've got two uncertainties. Both of them are going to lead to uncertainties in the composition of the crust and what nuclear reactions occur.
Yes.
But which one leads to the biggest uncertainty?
Right.
Right. So that's the one that you concentrate on reducing the uncertainty in first. Right. So that's the.
Which parameter results in the most uncertainty, the L parameter or the surface energy?
Yeah. Well, it's not the parameter that results in the uncertainty. It's the uncertainty in the parameter that results in the uncertainty. Like L, like if I knew L exactly, then there'd be no uncertainty in the composition. So it's not L that leads to uncertainty. It's So this is uncertain, this is uncertain, therefore what reactions occur are uncertain.
Yes.
And we want to know, like, if this is uncertain to 20% and this is uncertain to 20%, right? Or okay, let's put it this way. If you pretend that this is completely certain and you make that uncertain by 20%, and you find that that makes the composition uncertain by 10%.
Right.
And then you fix L and you make the surface energy uncertain to 20%, and that makes these results uncertain to 40%, then you know that although both L and sigma have the same uncertainty, if you're interested in modeling the crust, it's sigma that you need to work on first, like, because that's going to, narrowing the uncertainty in sigma is going to have the biggest impact. So that's the point.
Yes. Okay. Did I explain the finding that the uncertainty in sigma drastically, what did he even say? I had the sentence down when I was practicing, which was sigma results in the most drastic change, which means it would vastly. I'll practice it more. It was just saying that sigma was the one that had the most sigma had the most effect.
The uncertainty in
research.
sigma
Yes.
has a greater effect on the uncertainty in the crust.
Okay. So I just said research, yeah, in the crust.
Yes.
Okay.
Research, yeah, research is that's a vague word, so you shouldn't use it. Okay. Yeah, and so you should also mention, people would be like, well, why did you choose these numbers?
Okay. Yeah.
So you need to say those are representative, they're sort of, and it's actually, these numbers are kind of the baseline, not I think you said that these numbers were
the baseline
when it's these numbers.
Like I said baseline because these were the ones that we started off with. These are the ones that we messed around with. Okay. You're saying that these aren't?
Well, these are what, like, if you just told someone, make me a crust model, and they looked around in the literature and saw what most people used, they'd find it was this and roughly this. Right. But we're basically changing them both by about 30%.
Okay.
25 to 30%. Okay, cool. Yeah, so for the conclusion slide, you need to, well, there isn't a conclusion slide. So here you would have conclusions and then future work below it. And then the conclusion is the sort of headline message. The uncertainty in the surface energy of nuclei is more important when it comes to determining neutron star crust properties than the uncertainty in the nuclear matter parameters. And again, I think you got bogged down a bit trying to say this when really you can just say this. Like, you've got the words there already, and it's fine to. It's usually you don't want to read off slides, but if it's just you could paraphrase this, but the words are there.
Right.
Remember, the slides are there to help you. Like, they're your guide. They should tell you what you're going to say next.
Yes.
Okay.
The question. Hey, there's a symbol.
There you go.
There you go.
Excellent. Oh, one other minor point. So L doesn't appear in any of those equations. So you should say that L is a parameter in the model that we use to calculate
Yes.
this. And we're not showing you that model because it's a complicated thing that would,
go over.
In the time constraints, we don't have time.
Yeah, I like that.
Yeah.
Mm-hmm.
Okay, good.
Cool. Okay, so listen to this.
Yeah.